Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Panama Buena Vista Union School District, and Kern High School District, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon and welcome to Do the Math. I'm Michael.
I'm Devin.
And I'm Samantha. For math homework, help call in Bakersfield 636-4357. Everywhere else 1-866-666-366-284. Email dothemath@corn.org. We're online at dothemathonline.net. And on social media, Facebook, Instagram, Twitter, and YouTube.
All right, nicely done, Samantha. So where do you go to school?
Douglas J. Miller Elementary.
And what grade are you in?
5th.
How is 5th grade?
It's good.
Yeah? What's so good about 5th grade?
Well, those new math that I'm introduced to, right now we're doing like polygon, things like that.
You know what polygons are?
Yeah?
There are a lot of different types of polygons, aren't there?
Yeah.
Have you done anything with circles yet in class?
I don't think so.
Okay, well you probably will, and guess what? You're going to get a head start on it today. Does that sound good?
Ooh, yeah.
Ooh, yeah, there you go. That's exactly what I wanted to hear right there. So all of that social media stuff that you read down there, again, Facebook, Instagram, Twitter, and YouTube, what we do is we put out a problem of the day for everybody to look at, and then they submit their answers, and we see how they did on them.
Okay.
Should we take a look at it?
Yeah.
All right, let's take a look at today's problem of the day. So it says find the circumference, and we have a circle up there with the number 10 in it, and then it gives us a formula for finding circumference. Now, have you ever heard of the word circumference before?
Yeah.
What do you think that means, or where have you heard that?
I've heard it in GATE, and it has something to do with circles, either like the middle of the circle or like the very center of the circle.
Okay, so you're on the right track. So you know it has to do with circles, and you know that line. What is the line in the middle? Do you know what that line is called, the one that goes all the way across?
Circumference?
Well, the circumference is all the way around it.
Something that begins with an O, I think.
That's the radius.
Radius.
And that's halfway across.
Yeah.
So the diameter goes across all the way, and the radius goes halfway across. Mm-hmm. Does that make sense?
Yeah.
Okay. So the circumference goes all the way around the circle, like the perimeter of a polygon.
Okay.
And the diameter is what that number 10 is representing.
Okay.
So if 10 is the diameter and it goes all the way across, what would the radius be? If the radius only goes halfway, what would that measurement be? The whole length is 10, but the radius is only half of that. So what would half of 10 be?
20?
Well, that would be double 10.
Oh, wait, no, 5.
There you go. All right, so I knew you were in the right thing. You're like, yeah, you're at it quick, but you just went the other way, right?
Yeah.
Twos are involved somehow.
So the radius would be 5.
Yeah.
Okay, so let's take a look at the formula. It says circumference equals 2, and then it has the symbol for pi. Do you know what number we use to represent pi? It's a decimal. Have you ever?
Yeah.
What do you think it is?
3.1415.
Oh, easy, sister. I'm sure you got it memorized to 100 spots, but we'll only need a couple, all right? So we're going to go 3.14.
Yeah.
Sound good?
Yeah.
For today's date, 3/14. Did you know it was Pi Day?
No.
You did not celebrate this in class?
No.
Well, now you know it's Pi Day. Happy Pi Day.
Okay.
All right, here we go. Okay. So we have the circumference is equal to 2 times pi. So what I want you to do is go 2 times 3.14.
Just as an approximate. We don't have to go all the way deep.
And then hit equals. Then it says the next thing is R. And what did we say the R was, the radius? It was halfway
Halfway.
across. And if 10 is all the way across, what's halfway again?
5.
5. So we're going to go times 5 equals, and what do you get?
31.4.
There you go. So let's take a look at the options up there. So first of all, we have 10. Now, do we think 10 is the distance all the way around the whole circle?
No, because that's already only halfway.
Right, that's just the diameter going across, right? Look at the one under it, 3.14. What does that represent? Do you remember what that represented?
Pi.
Pi. Let's look at C. 5. What was 5 in this again?
Half of the radius.
Half of the diameter,
Diameter.
which is the radius. There you go. And then what do you think about number or answer D? 31.42. You think that's our answer?
I think so because it would
Just
be.
rounded it, right?
Yeah.
Yeah. All right. So what do you think? D is the correct answer?
Yeah.
Let's take a look and see if D is indeed the correct answer. And there you go. Nicely done. 1 for 1 on Pi Day.
Yeah.
There you go, sister. All right. Clear that out. So we have a lot of stuff going on today with pi. We're going to check it out in today's Math in the News. All right, today's Math in the News obviously is going to have to do something with pi, right?
Yeah.
Because what is today?
Pi Day.
It's Pi Day, right? And you'll always remember that, right? On 3.14, 314. Okay? And I think it was only back in the 80s, early 80s, when Pi Day actually came about, and they officially declared it National Pi Day. But we don't get the day off. But we don't want the day off because we have math to do, don't we?
Yeah.
All right, so happy Pi Day. So let's take a look at this. I found this very, very interesting. Do you know what symmetry is or what it means?
Yes.
What does it mean? What do you think it means? What's symmetry?
So when two sides are the same.
Very good. When two sides are the same.
Yeah.
Exactly the same,
Yeah.
right? If I cut this pie in half, it would be symmetrical because it would be the same on both sides, wouldn't it?
Yes.
But if I cut it a little closer to you, would it still be symmetrical?
No.
It wouldn't be the same, would they?
Yeah.
All right, so we'll go with that. So here we can see that symmetry, the quality of being made up of exactly similar parts facing each other or around an axis. We're not going to do rotational symmetry and stuff right now. We're just going to deal with symmetry. So we can see the letter A is symmetrical. Do you see how if we cut it right down the middle, it is the same on both sides?
Yes.
That makes sense. Do you think there are other letters that are symmetrical?
Yes.
What ones do you think? Can you think of any offhand?
O.
Oh, there you go.
Oh,
Can you think of it one more?
N.
N?
M.
M.
M. There you go. I would say M is also. All right, so here we go. So we take all of the letters of the alphabet. Okay, we're going to start up here at the letter A. And they're going to go all the way around like that. Anything that is symmetrical, we're going to cross out. So the letter A was symmetrical, wasn't it?
Yeah.
B isn't, right? And we want vertical symmetry.
Vertical symmetry. That's an
Okay.
important distinction to make because if you have a line across the center of the B horizontally, it would.
Then we would have a lot more.
Right,
But we're
exactly.
doing vertical symmetry only. So see, we don't have any other symmetrical letters until we get to H and I. And there's your M, right? There's your O. And then we have quite a few. T, U, V, W, X, Y. Those are all symmetrical letters. Make sense?
Yeah.
Now, if you look at this, you can see here are the ones that we have left. All right? So, can you make any, what do you think, like, if you saw that, could you make anything out of that? Not words, but is there any way you could associate that with anything else?
No, but other than that, E is the only vowel in though.
Oh,
Great
nicely done.
observation.
So E is the only one.
Good
right
pickup there.
So, if we have JKL, that's 3. N is, so we're grouping these together. All right, you see how C, B, C, D, those are all 6 letters together? And there they are, the 6. Right here we have 3. Okay, so JKL is going to be at the top, that's 3. 3 letters. Then we have 1 all by itself. PQRS, there's 4 letters. Then we have 1 all by itself, Z, and then we have these 6. So it goes 3, 1, 4, 1, 6. Does that bring to mind anything?
Pi.
Are you sure?
I mean, like minus the 6.
Well, why do you think the 6 would be there? Because it's rounded. You know how to round numbers?
Yeah.
Okay, so let's take a look at this. We have 3.1416, which is what this was, with all of the symmetrical letters taken out. So we have 3.14, and the actual pi is 5. But if we take the 9 and round it, it becomes a 6. Make sense?
Yeah.
That's pretty slick, don't you think?
Yeah.
If you take the alphabet, put them in a circle like that, and take all of the symmetrical letters that have a vertical symmetrical line out, then we're going to get pi. We get pi out of the alphabet. I just think that is awesome.
Yeah.
You like that?
Yeah.
Let's go 2 for 2 on Pi Day then.
Yay.
All right, there we go. I like that. You like that?
Yeah.
Good. You ready to do some more stuff? All right, let's take a look at another one. This is where you're going to have to do a little bit of work.
Okay.
Are you ready? So you and Devin head over to the board quickly.
Right this way.
And what I'd like you to do is put a circle up on the board.
Go right ahead.
There you go, nicely done. Now what I'd like you to do is I would like you to divide that circle into 4 equal parts so that you have it in fourths.
Okay.
Now Samantha, if I took one of those fourths and I divided that into 2 pieces itself, what size would that be? So go ahead and cut one itself. Now those 2 pieces, what size would that be? Each one of those little ones. And if you need some help, Devin's right there.
8.
So each of those is, you said an eighth, correct?
Yeah.
So you can go ahead and label them.
Each of these is 1/4. And we're going to say that a fourth divided into 2 parts, each of those parts is equivalent to 1/8.
Now Samantha, you knew that pretty quickly. How did you know that that was an eighth?
Well, first I was thinking it couldn't be in 6 because then the lines would be like arranged differently, and if you split 4 into 2 pieces, well, wait, no, when you times 4 times 2, it equals 8.
Well, you came about the right answer, and there's a lot of different ways to get to that answer, and you did it correctly. So what we're going to do is I did the same thing as you did, all right? So what I did is I had a circle, then what I did is I cut it into fourths, then what I did is I took one of the fourths and cut it into eighths. Now we're going to take all of those pieces and we're going to cut them apart, all right? So come on over here, and here are the pieces, so that we save a little time, that are now cut apart, all right? First of all, what I'd like you to do is put it together again so that it forms a circle.
Pretty quick.
All right, nicely done. So do you think you can use those pieces to form a rectangle or pretty close to a rectangle? So it may not be exactly straight all the way down on every side, but see if you can configure those pieces so that it comes close to looking like a rectangle.
All of the pieces?
All of the pieces.
No, that's circle again, right?
Yeah.
So
Did they each have to be like connected on the half, or
not
can I connect
necessarily.
them?
Oh, you can do whatever you
Play
want.
around with it, see what happens.
Keep going. You and Devin are going to keep working on that. You come up with as many different ways as you think and can move them around and see if you can come close to something that looks like a rectangle.
Now, in this instance, we want to make sure they don't overlap. So
Oh.
we still need them to be laid out separately. Okay. So you're still lining up with the radiuses touching, but you're alternating how they go. So one side has the curve, the arc facing up this way, the other side. Okay, so what about this remaining piece? Okay. Now, does this look like a rectangle, or is there another shape in geometry this looks somewhat similar to?
Like the typical quadrilateral.
Yeah, I could almost see this almost like a parallelogram almost, right? Where we have our sides up here, and then we have our diagonals to the side. So is there a way we might be able to turn this somewhat parallelogram into a somewhat rectangle? Maybe by moving one of the pieces around.
And I like that you made a parallelogram out of that, because that'll be a new challenge that I have for my kids when I said, hey, make a rectangle out of it. Then
You're
I'll
welcome,
say,
kids.
now rearrange them and make a parallelogram out
That's
of it.
right.
All right, so keep going, see if you can get the parallelogram close to a rectangle. So what are you thinking about as you're moving them? Are you thinking about particular pieces or in order? What are you thinking about?
I'm thinking of how can I make these round parts like not really count when I do this. Like it looks like a rectangle even though they're all round pieces.
Right, because
Right.
it is going to be rounded on the sides.
There's no way around that. So, is there a way that we can get the most out of the bigger shapes arranged in such a way that we are more flexible how to use the smaller shapes on the sides?
So there's your hint. So Devin just gave you a hint. The smaller ones, the eighths, will be at the ends. So those ones will be in the middle.
That's the same thing I did earlier, did I?
No, it's actually a little different. I believe that the last time you did it, one
Right,
of these
that's
pieces
pretty quick
was
too, right
in
there. The way
middle
she
there.
did that, pretty quick. As soon as those are the two
Wow.
ends, we just chop, chop, fast, fast. There you go. That was pretty awesome right there.
Yeah.
So let's take a look at the one that's up on the board under the camera here. And does yours, so we'll go to the camera one. And we'll see if it looks
There we
like
go.
that.
Yeah,
Yeah.
I'd say so.
That's exactly it, isn't it?
Yeah.
All right. So what can you tell me? Because we know that this forms a rectangle, right? Pretty close, right? Because if we do this, we can see that, all right, we could make a straight line going all the way like that. And we know that this is going to be a straight line down there. Now there's going to be a little bit of open area right here, correct? But basically, we can see that the rectangle can come from the circle. What can you tell me? What do you think, what do you notice about how that circle and the rectangle are similar? Did you notice anything? So let's figure out the areas of them, right? So we need the radius. So can you measure that side, that straight side for me? And let's do it with inches.
Like about 2 inches.
Okay, so it's 2 inches, all right? So what I'm gonna do is I'm gonna put up, so you guys can write this on the board over there.
Okay.
All right? So we can put R equals 2 inches. Now, in order to find the area of a circle, you and Devin talk about what that formula is in case you don't know it off the top of your head.
So we need to multiply that.
Okay, what are we going to multiply this by?
So 2.
Okay, so now, is this from the earlier problem we did in the beginning of the show?
Yeah.
Okay, now I think there's an important distinction we want to make in that formula. That formula, which was 2 times pi times the radius, helped us find the circumference of a circle, right? And if we think about circumference, we make the comparison to perimeter, right? The distance around the outside of a shape. However, we need to find the area. So how is the area of a shape different than its perimeter, or in this case for a circle, the circumference?
Because it's only the outside of a shape. When the area you're looking at everything that's inside of the shape.
Exactly. So in regards to the area of a circle, it's a little different because we can't do length times width with a circle, right? So there is another formula here. So to find the area of a circle, you would take the radius and you would multiply it by pi, and then with the radius itself, you're actually going to multiply it by itself, or you're going to square it. So for the area of a circle, the formula is pi times the radius squared. Do you know what it means to square a number?
Yeah.
Okay. What does it mean?
Multiply it by itself.
So multiply it by itself. Let's go ahead and break this down. If we multiply the radius of this circle by itself, and remember the radius is the distance from the center to the edge of a circle. Here we said that was 2. If we do the radius equals 2, what would be r squared, or what would be 2 squared?
4.
Right, so we have pi times 4. And if you remember, we had this equivalent, right? We had said that pi was equal somewhat, not exactly, right? So we're going to say about. We're going to do a squiggly equal sign. Pi is equal to about what? If we put it into a calculator or it has a number form, what would it be about equal to?
3.
3. Can we go a little bit further with the decimals?
0.141.
There you
We
go.
can stop right there.
We'll just leave it at today's
There
date
are
there,
ways
sister.
we know we can keep going. We only have an hour, though. All right, so let's go ahead and be somewhat equivalent to this. So what we're really saying is 3.14 times 4. And again,
And
this
here's
is an
your
approximation here.
Here you go, Samantha.
Go ahead and throw that into the calculator.
Oh, wait.
And in this case, what does that get us to?
12.56.
12.56 inches, and because it's area, it's squared. So what that means is the area of a circle with a radius of 2 is about 12.56 square inches. It's not quite 12.56 because we have all these extra decimal values
Yeah.
that we decided to just kind of stop at just to get close.
So now come on over and we're going to compare that to the rectangle that you have. So we know that the radius was 2, so let's go ahead and put that piece back where it was. So now imagine that you've got this rectangle now, okay? Measure, what do we know the bottom is going to be? What is that length?
4.
Well, take a look. Where does it end?
Like,
about 2, right?
Yeah, just about 2.
Okay, and let's do it this way. And approximately, what is that going to be?
6.
Okay, so if we had the length and width of the the rectangle, those measure 2 by 6. All right. So, how do you find the area of that rectangle now?
You multiply this.
Okay, so you'd multiply the length times the width, in this case 6 times 2. So what would be the area of this rectangle?
12 inches square.
12 square inches. Now, is 12 square inches close to 12.56 square inches? Would you say those two are not exactly equal, but are they close?
Yeah.
Reasonably, yeah, I'd say so. And so we're able to at least get close to what the area of the rectangle is through the arrangement of the pieces that we cut out of the circle.
So come on back over, Samantha. So have you seen the relationship between the area of the rectangle and the area of the circle?
Yes.
They're pretty similar, aren't they, right?
Yeah.
And it's pretty cool how you can take the circle apart and form it into a rectangle like that. So have you done some good work so far today?
I think so.
Do you think we're 3 for 3 on Pi Day?
Yes.
I think we are also. So for your great work so far, you've got yourself a meal courtesy of our friends at Grillin' Burger, so congratulations on that. I just saw Lydia the other night, and she said that a couple of kids have been bringing in their certificates, getting some great meals at Grillin' Burger, so hopefully you have an opportunity to do that. When you go, if you remember, ask for Lydia and let her know that you were on the show, and she'll set you up with whatever meal you like. Sound good? Mm-hmm. All right, and whatever goes with a meal, you need a little bit of dessert also, don't you think?
Yes.
So since it is Pie Day, perhaps we'll have a little pie. What do you think? Yeah, there you go. Everybody loves pie. There you go. Hey, you know what? We're going to check in with the Bakersfield Museum of Art after we learn a little bit about earth art. Absolutely beautiful, Earth as Art. We do have phone tutors available most Tuesdays and Wednesdays throughout the regular school year between 3:30 and 5:30. Every once in a while, we are fortunate enough to have somebody come in the studio and teach us a little bit about art and the math that goes with it. From the Bakersfield Museum of Art today, we have Curtis. How are you this afternoon?
I'm doing very well. Thank you again for having me on.
It's great to have you. I know you've been a guest on here a couple of times. Remind everybody, though, your role at the museum.
So I am the coordinator of guest services. So usually when you come in the museum and you get to the front desk, you get to interact with me, and I'm happy to take care of any questions or anything that you may need.
All right. And what will you be doing with Samantha today?
Well, today, Samantha, I am fortunate to have you as my assistant, but we will be making an abacus. Now, are you familiar with what an abacus is?
Yeah.
Yes? Okay, you were just telling me that you actually had one in your garage and you donated it recently.
Yeah.
Yep, and so this may look a little bit different from what you had in your garage, but it's very similar in how it functions. Now, do you know about how old the abacus is?
No, I didn't even know that the abacus was its name.
Yeah, it's called an abacus. It's great, or another name for it is counting tray. And it's a tool that mathematicians use to help keep track of very large numbers. But the abacus is actually about 5,000 years old. So we had this before computers, before iPhones, even before calculators. We had a tool similar to this that they used to keep track of very large numbers. And do you know how we keep track of large numbers with it?
The little beads that are inside the string.
Exactly. So if we have these bottom little beads, these ones count as ones, and the next row up would count as tens, because we have 10 of these. So if we were to count all of these, we would get one of these, correct? And if we count 10 of these, how many would we get after that?
100.
100. And if we had 100, if we had 10 100s, what would we get after that?
1,000.
1,000, yeah. So if we're counting really high numbers and we need help keeping track of things, then this is a great tool to use. So just really quickly, I'm going to show you how to make your own kind of low-tech calculator. Sound good?
Yeah.
All right. So I've given you some popsicle sticks, some pipe cleaners, some rubber bands, and some great beads. And the first thing we want to do is grab one of our popsicle sticks and one of our pipe cleaners. And we are just going to go about, half an inch from the top, and we want to wrap around that little stick, just like that. We're going to make sure that stays in place. We can wrap it nice and tight. Good, good. And then we're going to take our next one, and we're going to go about another half inch down, another inch down that popsicle stick, and we'll do the same thing and go ahead and wrap that around so it's nice and tight on that popsicle stick. Looks good. Same thing, and we're going to do that 2 more times. So we're creating our ones, tens, and hundreds rows for our beads. Now, do you think people still use abacuses today?
I think so if they don't have like a calculator at home.
Exactly. This doesn't require electricity. This never breaks unless you drop it and your beads scatter everywhere, then it kind of breaks. But usually they're pretty sturdy. Okay, do we have all of our pipe cleaners on?
Yeah.
Perfect. Okay, so now what I want you to do is take another one of these popsicle sticks, put it on the back there, and another one, put it on the front there. You can hold all of those together. All right. And then with one hand, we're going to clamp that down, just kind of put a little bit of pressure on it. Got it? Perfect. Yes, and we can take our rubber band, and we're going to wrap our rubber band around each end of our popsicle sticks. And that pressure is going to keep all of our pipe cleaners in line. Does that make sense?
Yes.
Yeah. All right, feel nice and tight?
Yeah.
Good. All right, now we want to start adding our beads to each of our rows, and we have 40 beads, so 10 apiece. Sound good?
Yeah.
19. This may take a little bit of time. All right, doing very well. So quick little quiz for you. So if I were to put 2 beads over here, 5 beads over here, 3 beads over here, and let's say 9 beads over here, what number is this on my abacus?
2,539.
Perfect. Oh my gosh. Excellent. All right, as we do this, so just a reminder to our audiences out there, the Bakersfield Museum of Art offers free admission every first Friday of the month from 10 a.m. to 8 p.m. The first Saturdays of the month, we offer free admission to Bank of America card holders as well as Merrill card holders. We have some great educational programs coming up with our Saturday studio as well as our spring workshops. Please feel free to check out our bmoa.org for information on that. All right, how are we doing? Pretty good?
Yeah.
Yeah. All right, doing very good. Almost coming to the end here of our beads. All right, and while Samantha finishes up over there, what we're going to do with the opposite side, we're going to do just like we did before. We're going to add another popsicle stick as well, and we're just going to wrap around our pipe cleaner. Make sure that's nice and tight around there. Beautiful. Mm-hmm. Very nice. And when you have those nice and secure on the other side, just like before, we're going to put the popsicle stick on the front and the popsicle stick on the back and secure that using our rubber bands. Looking very good.
Thank you.
Mm-hmm. And then we can just wrap around any additional material you might have with your pipe cleaners, just so it's a little bit cleaner looking. There we go. Looking very good. And what do you think our last step is when we are finishing up our abacus?
To write the numbers.
So we have a space for ones, tens, 100s, and thousands.
Well, I've got to say, Curtis, as Samantha is wrapping up finishing hers, that's a pretty creative way to make an abacus for students that are learning numbers and place value especially.
Absolutely.
And I can see how a lot of kids could get very creative with this, because you could do this in specific designs to be able to make things based on what numbers you may want to come up with, but just
Definitely.
the colors themselves.
Absolutely, yeah, you can get very creative with this. And the abacus is not limited to just, place values. You could do square roots with it. There's all sorts of different functions that you can do with a simple abacus.
Nicely done right there. So once again, Curtis, if somebody wants to know a little bit more about the museum, where do they need to go to?
Please visit us at www.bmoa.org.
All right. Curtis, thanks again, once again, for coming in. You guys from the Museum of Art are always coming up with some great ideas how to implement art and math at the same time. We do have phone tutors available until 5:30. We'll be back with more right after this.
Great.
Ever since the Victorian era, snowflakes have been revered as perfectly symmetrical, six-sided crystals, believed to be as perfect and pure as the heavens from which they descend. But what if this divine image just melted away? It's 1885 in Vermont's wintry terrain. 20-year-old Wilson Bentley is fascinated by snowflakes, so he attaches a camera to his parents' microscope to capture a photo of one. After countless attempts, he finally gets a clear picture. Thousands of pictures later, and Bentley's collection is dominated by what comes to be our iconic view of snowflakes. Each perfectly symmetrical, yet unique. Bentley even coins the phrase, "No two snowflakes are alike." Across the Atlantic, German meteorologist Gustav Hellmann and his associate Richard Neuhaus are photographing snowflakes as well. However, their photos reveal something entirely different. While each snowflake is unique, many are irregularly shaped, imperfect. It's said that Hellmann accused Bentley of altering certain photos. Bentley countered that any alterations were to remove dust particles or debris from the snowflake photo to show the flake as true to nature as possible. It's now present day in the snowy mountains of Utah, an area that thrives on winter tourism. It's here that NSF-funded engineer Cale Fallgotter and atmospheric scientist Tim Garrett have revolutionized the process of capturing photos of snowflakes to better study their fleeting existence. Predicting how winter storms will affect us depends on how we measure what falls out of them, but current methods are imprecise. Fallgotter and Garrett have developed a high-speed camera system specifically designed to provide the clearest pictures ever of free-falling snowflakes. They call their system the Present Weather Imager, the PWI. Composed of a single industrial-grade 1.3 megapixel camera and a built-in computer, the PWI uses an infrared motion sensor to photograph single snowflakes as small as 100 micrometers. A fleeting moment in time exists to gather data on a single snowflake. In the clouds, too soon. On the ground, and it's too late. So the PWI doesn't isolate or disturb the snowflakes. It waits for the perfect time, photographing them as they fall to the ground, mid-air, unaltered, providing data on a snowflake's size, shape, orientation, and even the speed at which it falls. And if researchers understand all of this, they can determine exactly what type of snow formed in the clouds above. Snowflakes have brief but complicated lives. They start when a super cold water droplet freezes around a speck of dust. This process alone results in Wilson Bentley's famous six-sided crystal. But it's difficult to discover one of these on the ground, because as a snowflake falls, it collides and freezes with other water droplets, a process known as riming, resulting in a little ice pellet called a grapple, the hard-packing snow. If a snowflake manages to dodge these water droplets, it will likely later collide with other snowflakes to form something entirely different, an aggregate, the light fluffy snow. So the PWI photographs falling precipitation and then classifies every single photo. Aggregate, grapple, sleet, ice, rain. Each type of precipitation affects road conditions differently. Projecting these, especially around the freezing point, is a current problem. But with the PWI's data, local transportation departments could issue better weather warnings, with the potential to save lives. The PWI also captures nature in its purest form. Common among snowflake photographers, Bentley hand-selected the most attractive snowflakes to photograph and rejected those less photogenic. What Bentley and many others did was spark the public's fascination and curiosity about snowflakes, leading to the PWI's modern-day answer to how to capture a snowflake.
And absolutely beautiful. There we can see another example of art with the earth. Pretty nice snowflakes, weren't they?
I know, they were beautiful.
They were beautiful. I find them fascinating. I mean, I could look at that stuff all day long and study about them and all the different types of snow and things like that. Did you like it when we had that grapple? It seemed like it snowed out the other day in Bakersfield.
I know.
It was like raining dipping dots, right? Yeah.
Was it? Did you get a chance to go outside during that, or did you guys stay inside?
No, we actually went outside.
Oh, good, because I know that my kids, as soon as it happened, I go outside and go check
Because you don't know if
everything
it's
out.
hail or not, so what's falling on the heads, who knows, right?
Yeah, they'll be fine. They'll be fine. It's only weather. So doing that abacus, did you like doing that?
Yeah.
You learned a little bit over there?
Yeah.
Here we go, 4 for 4 on Pi Day.
Yay.
All right, there we go. We'll get you next time, brother. We'll get you next time. All right, so Samantha is a 5th grade student from Miller Elementary. And do you know who that school is named after?
Douglas J. Mello?
Correct, that is the full name of the school name. But do you know who he was or what his role was?
Not really.
He was the superintendent of the Panama school district in charge of the whole district. That's pretty cool, don't you think?
Yeah.
Yeah, that is pretty sweet. You ready for more circles?
Yeah.
Because what day is it?
Pie day.
It's Pi Day. There you go. So let's do some more circle work. Over to the board, young lady. So you and Devin are going to work on this. We see that there are 10 clues, 10 things that we're trying to find. But there are more than 10 figures over there. There are 12. So will all of them be used?
No.
You positive? Do you think some might be counted to satisfy, like we could use 2 of the things to satisfy one statement maybe?
Yeah, maybe.
Maybe. Well, you and Devin go ahead and get started on it.
Now, you don't have to do these in order, but if you find one that you can easily connect, we can go ahead and start with that one. So which one would you like to start with?
I could start with number 1.
All right. Which of these has 3 circles with the same center?
So this one is crossed out because it has 2.
Right.
It has a bunch of them. Only 2.
So we can narrow it down. We can look at shapes that have 3 circles and start from there.
That would be this.
Okay. Well, let's label that one, right? This meets
Yeah.
the conditions for 1 because you have 3 circles nested into each other and they all share the same central point. Okay, so that meets number 1. We can come back and see if there are any others that meet number 1 as well. But let's see about any of these others here. So let's just label and we make sure that we have L as one of these.
Okay.
Which is the next one you'd like to try?
8.
Let's take a look at 8. 4 equal circles. Now, we don't have any labeling here, but we can use estimation to get close to what this might entail. Now, which one of these has 4 equal circles?
I.
Okay, go ahead and label that as number 2. I'll put that. I feel like we're good on that one. Yeah, we have 4 circles. They're very similar in size. Let's go ahead and label that one. Now, question. Oh, actually, we're going to be down here. Question about this one here. This is number 8. So I, right? Now, question: does it have to be exactly 4 equal circles, or does it have, or could it include 4 equal circles?
Yeah.
Yeah, what?
Yeah, as in I'm agreeing with you.
Oh, I always appreciate people who agree with me. I just want to make sure that I'm accurate when I make a statement that people agree with.
Yeah.
Let's come back to that. Maybe if there are other shapes that have more than 4 circles, we can say that there are 4 there. All right, let's take a look at some of these others here. Let's pick another one. Now, there's something I do notice with all of the ones that remain, is that they have something in common that we'll also be looking at. So what do you notice with all of these remaining definitions?
They all end with the word intersecting points.
Yeah, they all involve us with a certain quantity or amount of intersecting points. So before we dive in, let's talk about what an intersecting point is. Let's take a look at, for example, C. How many circles do we have in C?
2.
Now, among those 2 circles, how many intersecting points do we have?
1, 2.
So intersecting points are points where the 2 circles cross over.
Yes.
Okay, well, we did a lot of work on C just there. Let's see if there are any where there's 2 circles that have 2 intersecting points. Now, I see one right here, but I also see this part, 2 unequal circles. Do these circles look unequal?
No.
Okay. So I don't know if C applies with 3 here, but is there a diagram with 2 unequal circles that have 2 intersecting points?
Ooh, possibly E.
Ooh, let's see. Are those circles equal?
No.
No, this one seems to be smaller, so this would be unequal circles. And how many intersecting points do they have?
1, 2.
So does this, it looks like a bear, does that fit the definition of 3 here?
Yes.
Okay, let's go ahead and label that. I like that. I'm going to say that 3 is E, and you're going to say that E is 3. All right. Let's take a look at B. Does B fit with 3 as well? 2 unequal circles with 2 intersecting points?
No, I only see that the lines connect like over here.
So we have two unequal circles with only one intersecting point. Do we have any definitions that meet that criteria? Two unequal circles with one intersecting point?
E again?
Yeah, so what about, look at two here. Two unequal circles, we have that, smaller, larger, and one intersecting point. So I think that B meets 2. You want to put 2 next to B on that one? Great. Now what about H? I see for H, yeah, that's going to be 8. I see for H that we have one intersecting point, but are those unequal circles?
No.
So these are two equal circles, but they only have one intersecting point. Does that look like any of the others that we might have here?
6.
Oh, I think that looks like 6, right? So 6 is going to be H. Go ahead and put 6 for H. All right, I feel like now we can start looking for some of these others. Should we start going in order to see which ones might be easiest to get to first?
Yeah.
So which one of these might be the easiest?
3 unequal circles.
3 unequal circles with no intersecting points. So let's see if we can find anything that fits that definition here. Ooh, I like F, right? Because each of these circles, as we go further outward, is larger. And I don't see any intersecting points there. So I think that you might be right that F meets the definition of 7 here. But I don't think that's the only one. I think there's another one that might fit the same criteria. It might be L, yeah, because we have 3 unequal circles, no intersecting points. Now they share the same circle. They share the same center, but it also fits out with 7 here. So I feel like 7 also fits L. Very interesting. And great job with the ampersand. Underutilized character to represent the word and. Nicely done.
Thank you.
All right, let's take a look at some of these others now. We have 4, 5, 9, and 10. Which one might we want to try now?
Number 5, maybe?
Yeah, I think you're looking at the ones that have the fewest intersecting points because they're going to be the easiest to identify. So we're looking for 3 unequal circles with 1 intersecting point.
Okay.
K looks great. Unequal circles, 1 tangent point right there. So let's go ahead and mark that. K is 5. We're coming close here.
All right, so we're going to end it right there. So kids at home can keep looking at that. But Samantha, you've got business over here.
Go do business. Nice work, Samantha.
Thank you.
So first bit of business. Did you learn a little something today?
Yeah.
What did you learn about? Basically, overall, what did you learn about today?
First of all, that today is International Pie Day.
There you go. That's the most important thing, right? So it is Pie Day.
Second of all, that a rectangle has so much in common with a circle.
There you go. And that the only way you would ever found that out is by actually manipulating those pieces around, right? And actually doing it and seeing it and calculating it. And you can see how those two are relatable, right? And what did you think? This was your first time you ever had apple pie. You like that?
Yeah.
What's the most familiar taste that you had with that? What was the
Cinnamon.
cinnamon, right? The biggest flavor right there. So you think it was a good day overall?
Yeah.
All right, let's have one more. Happy Pie Day. You say Happy Pie Day to everybody?
Happy Pie Day.
There you go. And what day is it always on?
March 14th.
There you go. Never forget it again. Until we meet again, continue to do the math.
Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Panama Buena Vista Union School District, and Kern High School District, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.